Hello! Let's continue our discussion of chemical kinetics. In our last video we looked at steady state approximation and how we can use that to determine rate expressions for reaction mechanisms involving several steps. In this video we'll look at another approximation method called the pre-equilibrium method that allows us to approximate rate expressions under certain circumstances, and we'll examine the temperature dependence of reaction rate constants. So let's first take a look at the pre-equilibrium approximation. In this case we consider a reaction where we have reversible steps. So we'll notice here in this generic situation we have A plus B going to I, which may reverse to go back to A plus B. So we have a reversible reaction mechanism. And then we have I in the second step, or the third if you wish, going on to react with a reactant D to form our product E. So we have this reversible process in which I is an intermediate. Now, if we are looking at the rate at which our product E is produced, we'll note that it's produced in this third step, which gives us a rate expression of K3 times I, the intermediate, the concentration of I, times our concentration of D. Now, in the pre-equilibrium assumption, we're going to assume that the consumption of the intermediate in this last step is very, very slow. So if that last step is very, very slow, then what we'll have in the first steps, the reversible step, is essentially an equilibrium. The situation would be that I is consumed so slowly that the first reversible steps are allowed to establish something close to an equilibrium, and we're going to assume that we're establishing an equilibrium here in this situation. Now, if that's the case, of course, we know that in a reversible reaction in equilibrium, the rate of the forward step is equal to the rate of the reverse step. So therefore, we have K1 times A times B for the forward step, and that's equal to K2 times the intermediate concentration in a reverse step. Again, that would be the definition of an equilibrium. All right. So we can solve for I in that expression to give us what we have here in this situation. We now have a concentration with respect to I, which we can substitute into our expression for the production of our product E to give us an overall rate expression shown here in this situation. So that is how we'll apply the pre-equilibrium approximation. Note the difference between this and steady state. In the steady state approximation, intermediate consumption is assumed to be very, very fast, and in the pre-equilibrium approximation, this last step is assumed to be very, very slow. So we will get different results in these two approximation methods, and which one is actually closer to reality depends on the actual rates of these individual steps. Alright, so now let's take a look at a situation that we've already examined with regard to steady state, and that's the ozone decomposition process. In that last video where we discussed the steady state approximation, we had this mechanism where we had a reversible step associated with ozone dissociating to O2 and oxygen, and then of course that was reversible. So if we let this step where the ozone reacts with oxygen, if we allow that to be very, very slow, the oxygen atom of course being the intermediate, then we're going to have essential equilibrium for the reversible reaction for the decomposition of ozone. So we'll just simply follow the same rules we did before, and again, going back to our discussion of the steady state approximation, remember we used rates rather than writing out the entire expression, at least initially, to help streamline the process. And so here we have the rate of change of ozone, where it's consumed in step 1, so negative R1. It's produced in the reversible step 2, so that's plus R2, and then it's consumed in the step 3, where it reacts with the oxygen atom. So that's why we have that. Okay. Now, again, because we have equilibrium, the forward reaction R1 is equal to the reverse reaction rate R2. And if that's the case, then we'll note that in this expression for ozone change, those two terms will cancel, and we're very simply left with the rate of change of ozone is equal to negative the rate of step 3. Okay. Now, that, of course, then gives us the rate expression is negative K3 times O, which is the intermediate, times concentration of ozone. So now, in order to complete this, we need an expression for the concentration of the oxygen atom. And we go back to our initial step, initial equilibrium, noting that rate 1 is equal to rate 2. And so we write that rate 1 is K1 times concentration of O3, and rate 2 is K2 times concentration of O times concentration of O2. We solve for the concentration of the intermediate, just a little bit of algebraic rearrangement here, and this is what we get. We then substitute that expression into our rate expression for ozone, and we get this final expression here for the rate of change of ozone with respect to time, based on the pre-equilibrium approximation. Again, if you go back to the steady state assumption, you'll find that there is a slight difference between these two expressions, again because the assumptions are different. Now let's move on to a different discussion, and that is the temperature dependence of rate constants. You're probably already aware of the fact, and it should make some sense to you, that if we increase the temperature, then the rate for a chemical reaction will also increase, and that should just make sense based on our previous discussions going all the way back to general chemistry. The question is, what are the factors that affect the temperature dependence of the rate constants? We immediately might think of collision frequency, the rate at which molecules or atoms collide with each other. Certainly in a bimolecular reaction will influence the rate of that reaction. If they're colliding with a greater frequency, one would expect the reaction to go faster. And that is indeed true. But there's another factor which is important, and that's a collision energy. There is a certain amount of energy that's necessary in the collision that in order for a reaction to proceed. And if the colliding molecules or particles do not have sufficient energy, then the reaction will not proceed. And it's this latter term, the collision energy, which is more important when looking at the temperature dependence. It has a far, in other words, it has a far greater temperature dependence than collision frequency, and it's the most important factor when determining how rate constants will change when we change the temperature. Okay, so you probably also remember that this collision energy is called the activation energy, which is, of course, the minimum energy necessary for the reaction to proceed. And that the probability that a collision will exceed this activation energy is given by this simple exponential expression, where E sub A in this expression is indeed the activation energy. T, of course, would be the temperature in kelvins. Then if we put this in an equation, which is called the Arrhenius equation, we find that the rate constant is proportional to this probability. Here we have K being the rate constant, and this term A is a pre-exponential factor, and it's generally assumed to be constant, meaning that we're assuming that pre-exponential factor does not depend on temperature. In fact, there are sometimes we do see a subtle dependence on temperature in reactions, and we'll talk about how we approach that a little bit later. Alright, so here is the curve that you've seen before representing the activation energy. We have reactants, of course, on the left, okay, and products on the right, and we're plotting versus the reaction coordinate. Right? We'll note that E sub A is the activation energy for the reaction going from reactants to products. If we're looking at the reverse reaction, for example, if we do have a reversible reaction, then we'll note that E sub A prime would be energy necessary to go back from products to reactants. So this is our energy diagram. We'll also remember that at the maximum in our energy we have what's called the transition state, and the nature of the collision complex that occurs for the molecules proceeding from the reactants to the products is referred to as an activated complex. Now, if we look at this business about collision frequency, or excuse me, the collision energy dependence, on the right side we have our activation energy curve with the reaction coordinate, and here on the left what we have is a plot that shows the fraction of molecules with a specific translational energy as a function of temperature. So we'll note, for example, at 200 Kelvin that we have this curve here, which shows that the vast majority of molecules, we actually have a maximum right here at this point, the vast majority of molecules do not have sufficient energy to surmount the activation curve. And in fact, if this is the energy necessary to surmount that curve, it's only a very, very tiny amount that would be able to do it. So at 200 Kelvin, this reaction would proceed very, very slowly, if at all. On the other hand, if we go to 500 Kelvin, we'll note that we have a much greater percentage of molecules that exceed the activation energy, and that's indicated by the area under the curve with the hash marks here. There are far more molecules that exceed the activation energy, and so because raising the temperature we've increased the energy of the molecules, we have a lot more molecules that can exceed that curve, that activation energy. The reaction is going to go a lot faster at 500 Kelvin than at 200 Kelvin. So we'll see here how that probability, that fraction of molecules with sufficient energy, is important in determining the overall rate constant for the reaction. All right. Now going back to the Arrhenius equation here, we can actually, if we take the natural log of both sides, we can see that we get a natural log of K equal negative E sub A over RT, and that if we plot the natural log of K versus 1 over T, according to this expression, we should see a straight line where the slope is just negative E sub A over R. So by plotting the natural log of K versus 1 over T, we'll actually be able to determine the activation energy for a particular reaction. Again, this assumes that the activation energy is independent of temperature. For a lot of reactions, plotting over a reasonable temperature range, we'll find that we do get a linear plot here, and that we can calculate the activation energy as such. But there are certainly circumstances when we'll find this is not the case, and the activation energy may indeed depend on temperature. So how do we deal with that? Well, going back to our equations, we have the Arrhenius equation, natural log equation here, and we can clearly see that based on this equation, particularly the slope, this would correspond to the slope, an instantaneous slope of a plot of the natural log of K versus 1 over T, that if indeed we don't have a straight line, if we have a situation where the slope is not constant, then the activation energy will be different at different temperatures. Or it could actually be that our pre-exponential factor is also dependent on temperature. So a curved line here could indicate the activation energies depends on temperature. It could indicate that the pre-exponential factor depends on temperature. It could indicate that both depend on temperature. So the analysis becomes much trickier at that point. We can certainly look theoretically, and there are several theoretical models that have been used to determine more precisely the temperature dependence of our rate constant, and this is a common equation here that we see where we actually have in the pre-exponential factor, you'll note that we have a temperature dependence, and we have the temperature dependence raised to some power m. The specifics associated with with the temperature dependence involve the collision frequency factor, as well as steric factors, which relate to the orientation of the molecules when they come together for collisions. If the molecules aren't oriented properly, then a collision, even though it has sufficient energy, may not yield products. They have to come together in proper orientation. So we need to take that into account when looking at more detailed effects of temperature. And in this particular equation, when we look at the temperature dependence, in most cases, most theories would predict that this exponent m is equal to 1. So that we do have sufficient theoretical foundation to begin to deal with a situation where we have temperature dependence which is more detailed and nuanced than that which you would expect from the simple Arrhenius equation. Right, so this ends our discussion of pre-equilibrium assumptions and the temperature dependence of rate constants. Stay tuned for more discussions of more complex reaction mechanisms and the corresponding kinetics.